Okay, so thanks for being here today. So today, indeed, we'll talk about deep learning for combinatorial optimization, and some of the work I'll present today is with my co-authors here. Okay, so let's start. So we're talking about deep learning for combinatorial optimization. And actually, my favorite example of a combinatorial optimization problem is the traveling scientist problem. And we actually wrote a paper about this 2 years ago, and this was also the topic of a very nice talk on Monday. So I will quickly recap the way in which this works. So we start with a problem instance, and then we input this into a neural network. Right, and then a neural network, it's going to predict basically where we should move next, and then we can feed back this partial solution back into our neural network, and it's going to tell us where we should go next. And in the end, and this is going to create a solution to it, right, which gets us well, basically back as fast as possible to the coffee corner. And now, so this was 2 years ago that we wrote this paper, which was actually a follow-up on earlier work along the same lines. And a lot of things have happened in the meanwhile. So, for example, scientists, they don't travel nowadays, right? And so technology changed, and we can teleport actually directly to the poster of your choice with this virtual conferences. So that's actually very interesting, because that was exactly the use case this algorithm was designed for, right? Because we can just retrain the model, and then well, it will basically learn by itself that it's completely irrelevant and by now what should be your order. On a bit more serious note, I want to have a bit closer look on what's actually the motivation behind using this solution methodology. So as we have also seen in the talk, I guess, on Monday, it's easy to make this parallel to, for example, machine translation, right? Or trying to get good translations by predicting actually translation for some sentence we want to translate. And if we compare this to combinatorial optimization, then we can consider, or we can at least approach a combinatorial optimization problem as trying to predict a solution for a problem instance that we have. But what I want to say is we should be very careful if we're going to do this, because actually those problems, although we can use like the same strategy for solving them maybe, they are not the same. And so let me elaborate on that a bit more. So if we consider machine translation, there's actually different aspects to the problem, right? So first and foremost, there's a problem of what I call to score the translation. So knowing whether a certain translation is good, right? So this is a learning problem. This involves data and the model. And then secondly, there's the problem of actually given this model, finding then a good translation, which is then purely a computational problem of finding the best translation. And if we compare that to combinatorial optimization, for example, then knowing actually whether a solution is good, that's just evaluating the objective function, right? So this is part of the problem specification. So it may be still expensive to compute, but there's no discussion possible on what this should be. So that's actually not really a problem. And it's purely a computational problem, I would say, of then finding the solution which somehow optimizes this objective function. So that's purely computational. And if we go a bit deeper into what that means that if we consider, for example, translation, right, the main thing we care about is to maximize quality. We want to get as good translations as possible, and then computation, it's a secondary issue. And that's why we also see that nowadays we have these huge models because we just want to get the best translations possible, but that's a secondary concern in computation. Whereas if we're going to look at combinatorial optimization, then our main goal is to optimize the cost, right? But we can't view this independent of the computation we're using to do so. And the reason is that if we're going to put like this two axes, so the computation and like the objective we're trying to optimize, then if we have machine translation, there's basically more aspects to the problem, right? If we invest more computation, we use bigger models, it's not a guarantee that we're getting better quality. We also need more data, we need to prevent overfitting, etc. Whereas if we consider like a purely computational problem, like combinatorial optimization problem, then, well, unless we're doing very stupid things, it's trivial to get better solutions if we're just going to invest more computation into that. And so we can even take that into the extreme, right? So if we let this curve maybe belong to some intelligent algorithm, then if we're going to use more and more computation, then ultimately we should find the optimal solution. But the same is actually true if we're just going to do very naive exhaustive search, right? So my point is here, if we have more and more computation, if we could have infinite computation for free, then the task is basically trivial, right? Even random search would give me an optimal solution. So the goal, what we're actually trying to achieve, is to push this curve, right? We want to find better solutions, but we want to use less computation in doing so. And so what's the way that we typically try to do this with neural combinatorial optimization? We're using neural networks, right, to parameterize maybe parts of our algorithms, which then help to make better heuristic decisions. And in doing so, we are actually adding computation to our algorithm, right, to evaluate these neural networks. And we're doing that to somehow reduce this computation, to get better solutions more quickly. And so I'm not giving you financial advice here, but this is an investment we're making. So we're investing to evaluate these neural networks, and we should better do this in a way that we actually see a certain payoff from that, which earns back this computational investment. And so I was thinking, well, what's the way we can put this into some along some axis that we can think about this. So I think on the first axis we have the amount of computation which we are going to use for evaluating our neural networks. And then on the second axis, we have the impact that we get from these neural network evaluations. And then if we look back at the example from the start of my presentation, right, where we're trying to predict a solution for a traveling salesman problem, then I would say, well, this is relatively cheap. We can just evaluate the neural network and it gives reasonable quality. Like, I think it's impressive what it can do, but obviously we can do much better solutions. And we realized that we can also use this model and we can just sample many solutions. And then obviously we get better quality solutions, but we also increase the computational cost for doing that. And then there's other ways to, well, combine neural networks for solving optimization problems. So, for example, an idea is to do learning to search. And, well, we can have a discussion on where you would maybe put this along this axis. But obviously, if we're going to learn local search operators and if we're going to learn good operators, then these have a high impact on the quality that your algorithm will deliver. But if we have to evaluate a neural network for each and every iteration of a local search, right, and this can be like tens of thousands of iterations, then we're also putting in a fair amount of computation. Also depending, of course, on the size of the network that we need to run in each iteration. And well, like we've seen today, also there's, for example, the learning to branch is another line of work where I think that's very promising as it comes across to me, because like the amount of branching decisions we need to make is relatively small compared to the overall amount of computation, right? Because most of the time it's just spending in like solving relaxations or primal heuristics. So, but on the other hand, there's a high impact if you make good branching decisions. That is pretty clear. So this, to me, sounds like we can have like a high impact with relatively less computation, and that's why we're seeing the promising results here. As well. And for me, fortunately, it was hard to come up with an example, which would be on the lower right here, which I think means that, well, sensible things are being tried. But obviously, my point is that I think the aim should be to get more towards the top left, right? So we should design our algorithms or augment them with neural networks in such a way that we can invest like relatively little computation maybe and get most of the impact out of the neural networks that we're using there. So to put that in a bit more fancy way of saying them, I think you should count your flops and make them count. Okay. So now if we go back to the example from the start, right? So this was the attention model, some of you may know it, which we presented some years ago. So this was an encoder-decoder type of model for a traveling salesman problem. So we have an instance, we put it into an encoder, we get some embeddings for all the nodes in our problem, and then we can generate many samples from that actually. And you may see that the samples are the same here. That was because I was lazy in editing the slide, but that is something that can happen, right, if you sample with placement. So if you find that a problem, you should look at one of our other papers. But the main point is here that if we're going to try to sample different solutions, we need to run our decoder for each solution for every step, right? And that obviously adds a high computational cost for generating all this solution. And so that's why I was very excited to actually find a different paper on the traveling salesman problem, which was by Joshi et al., also from the presenter on Monday, actually, where they use the graph neural network and they take a single step approach where they take an instance input and predict a heat map of edges all in a single step, and then use a beam search on top of this to decode this into a valid TSP solution. And if we're going to make image comparable to the slide I've shown you previously, this means that we just need to run our neural network once, right? And it's a much bigger neural network maybe, but after we've evaluated this neural network, we can take many more samples for the same computational budget, because we don't need to evaluate our neural network anymore for each of these samples. So this actually got me really excited, because I think it's impressive that we can get this information out of such a neural network. But I think there are better ways in which we could leverage this, right? So the next thing I want to talk with you about, something which has come across also a few times in the past days, is dynamic programming. So if we go back almost 60 years, then there's the classic HealthCarp dynamic programming algorithm for the traveling salesman problem, which is nicely summarized in this recursive formula. And so in this formula, we have S, which represents a set of visited nodes, and I, which represents a current node where we can be. And this together, I refer to as the dynamic programming state. And then this function, which we define here, it defines the minimum cost to go from your start node to to the current node, visiting all of the nodes in this set, right? And this formula, it expresses this recursively in terms of the cost or the distance between two nodes. And actually what this minimizing operator is doing here, it means that this function for each dynamic programming state, so for each set of visited nodes with the current node where you can be, it's selecting the best solution. So we see an example here where we have two partial solutions for the TSP problem, where we visited the same set of 4 nodes, and we currently are at the third node, at the same node, and we can clearly see that the left solution, it's a better solution than the right solution. And this means that the right solution can never be part of an optimal completed solution, because they have the same remaining nodes to visit. And so in terminology, I would like to put it, we say that the left partial solution actually dominates the right partial solution. And that's very nice, because what basically the HealthCarp algorithm is doing, it's considering the complete solution space. It's actually considering all possible solutions, so doing a brute force, but by removing these dominated solutions, you can drastically reduce that space. So you can go from factorial size space to exponential, basically. And the way in which we typically look at this, well, if you look at this recursive formula, then this is a backward view of the problem, right? So it expresses the cost of a solution in terms of the cost for smaller partial solutions. Whereas typically if we do a brute force or like a sampling-based approach, like from a neural network model, then we have a forward view. We try to incrementally build a solution. But actually these two views, they align pretty well, because we can also execute the dynamic programming algorithm in a forward way. And then what is actually the difference between doing like brute force search over the full solution space and doing dynamic programming over the dynamic programming space is that if we would do it in a breadth-first manner, at every iteration, we simply remove the dominated solutions. So this gives an equivalence actually between the DP algorithm and the full brute force algorithm. But still, unfortunately, this complexity, it's impractical, right? We can only do this for moderately sized instances. So there's something we can do there. And that's like deriving a heuristic, basically, of these approaches by somehow restricting the solution space or the search space that we're considering in this algorithm. So one thing we can do, for example, instead of a brute force, is use a beam search. So we're going to do a breadth-first search, but at every step of the process, we're only going to expand the limited number of expansions equal to B. then obviously we are only considering a small part of the search space. But if we do this in a clever way, then we may still get a good solution. But now the computational cost will be linear in your beam size or the number of nodes. And we can do the same actually for the dynamic programming algorithm, which makes it an instance of restricted dynamic programming. And this will drastically cut down the search space, but we can still leverage then this knowledge on how we can remove dominated states in between, or dominated solutions. But obviously, the question is, how do we define this restricted search space that we are going to consider? So we need somehow a policy to make this selection of the states that we're going to expand. And I guess you can feel it coming, because we're on the deep learning for combinatorial optimization workshop here, but we propose to use a deep neural network for that, and actually like the neural network from Joshi et al., which I just have shown to you. And so the way then the overall algorithm works, or after it's trained, so this would be the test time procedure, is for each iteration, we're going to start with an empty TSP solution. We're going to expand all the solutions that we have. Then we're going to remove the dominated solutions according to our domination strategy. And then we're going to pick the top B according to the policy, which I will define next. And this we're going to repeat until we've moved through our complete solution space and then found a complete tour. And so what does this policy look like? So basically this policy, it selects the top B, so if we have a beam size B of the solutions that maximize the score, where the score is something we manually defined as a function of this heat map, which was predicted. So it's basically the sum of the heat in the axis of your partial solution, plus some estimate of the heat that you will still acquire when you're going to complete that solution. So that's somewhat similar to how a star search algorithm, for example, uses also prioritizes its search. And the reason that we do this is that if we would only look at like the heat, or like the quality of the axis in the partial solution, then this may be very high, but it may, as you can see in this example, skip certain nodes, which is obviously not a good thing to do. And by including actually this potential, we can realize that if we skip certain nodes, we remove promising edges as well by doing that. And this will avoid this pitfall. And as a small comment, so if we would use the autoregressive approach, which I've introduced in the beginning of my talk as well, this would not suffer from this problem. So we see that this model is very good at like not skipping nodes. So this is really because we restricted sort of the expressivity of the model by predicting all the edges at the same time, right? It cannot make like this conditional predictions, but this is a way in which we can actually solve that. And the nice thing is that if we do this, we only need to evaluate our neural network once, right? So we just have the instance, we can run it through our neural network, and we get this heat map prediction. And then by defining this function, we have a very cheap way to score a partial solution, and it means that we can run a very large search algorithm on top, comparing to using a neural network maybe in every step and for every partial solution that we have. Okay, so that basically summarizes our deep policy dynamic programming algorithm, and it has a number of advantages. So first of all, dynamic programming is a very flexible framework. So I explained it for TSP, but it's actually pretty easy to do this for VRP, so for an capacitated vehicle routing problem. But since the dynamic programming algorithm constructs actually the solution in order, you could say, it's also much easier to take into account like practical constraints such as time windows. And secondly, this is very suitable also for GPU accelerated implementation. Like everything can be computed with low-level tensorized operations. And this algorithm provides a natural trade-off also for the computation versus the performance by varying the beam size, right? And if we make the beam size large enough, then we get our guarantees that we have an exact algorithm. And the advantage is that if we can train this model in a supervised manner. So we just need a set of example solutions, which we can train once. Then we can train this model to predict actually the edges in the example solutions. And then at test time, we can just run this dynamic programming algorithm. And it means that we only need to evaluate our neural network once. So that's a nice way to get lots of benefit from this evaluation, but at a relatively small compute. And so now I hear you thinking, well, I don't actually hear you thinking, but I've invested this time in listening to you, so show me what we get then. So we implemented this algorithm for the traveling salesman problem and for the vehicle routing problem and for instances of 100 nodes. And then for the traveling salesman problem, we actually used a pre-trained model from this paper I mentioned. We see that we get pretty much optimal results, which is because well, we actually get like very sparse graphs which contain the optimal solution with high probability. And then for the vehicle routing problem, we compare against the LKH and a lot of recent neural approaches as well, and we see that we can really cut down this gap to LKH, and even if we run like with a beam size of 1 million, we could even slightly improve on the solutions which were found by LKH, admittedly with a slightly larger runtime. And as I said, this should always be considered as a trade-off, right? So that's why we also did a study where we also allow LKH to use more runtime, so generate multiple solutions. And then we see that we can actually also form a stronger baseline. And I wouldn't say that we like beat it in terms of performance, but I would say it's pretty reasonable for like this first try of a general framework of using this dynamic programming algorithm compared to a highly optimized solver. And of course, we have to account for how we compare like CPUs and GPUs. But we're actually getting, well, I would say reasonable performance and pretty close that this can get really interesting. Some ablations we did to see like which components of our framework actually make up these results. So in the red line, you see the full dynamic programming algorithm with the heat and the potential. In the green line, you see what happens if we indeed remove this potential function, then we see we get much worse results. And in orange, you see if we wouldn't use dynamic programming, but a simple beam search using this same policy function, then we also see that this makes a huge difference. And in blue, we see what would use if we just take the cost of the current solution instead of the heat map to score like the solutions we want to expand. So this is really like a classical instance, you could say, of restricted dynamic programming. And then you really see there's like a difference of like 15% in terms of the objective value that you get. So yeah, that's about my talk for today. So I think I tried to hurry up, but in the end, we have 2 minutes left, so that's nice. But the message for would be so to always think about count your flops and make them count, right? So invest your computation right. And so I'm happy to take the questions.